Welcome to The Explainer. Today, we're pulling back the curtain on the secret language that powers basically everything you do online. Every search, every filter, every single recommendation.
I mean, you've wondered this, right? It feels like actual magic. How do you find one specific piece of information when it's just a tiny drop in a massive ocean of data?
To figure it out, we're going to follow this little roadmap. We'll start with how we even ask questions of data. Then we'll look at SQL, which is the language we use. And then we'll get to the really cool part, the secret grammar that makes it all work.
Right, so to find that one specific fish in the ocean, you can't just shout into the water and hope for the best. We need a really precise way to ask our question, a language that the database can actually understand.
And that tool, that language, is called SQL. It's pretty much the universal way we talk to databases, and you know what? It's built on a surprisingly simple structure.
So, take a look. A basic SQL query has this really clear logic. You select the columns you want, you say from which table to get them, and then you add a where clause to filter down the results. It's our way of describing exactly what we want from the database.
But to truly get what's going on, we need to ask an even deeper question.
I mean, really, what's the logic it's using to follow our instructions? Well, it turns out SQL isn't just a random set of commands. It has this secret underlying grammar.
And that grammar has a name, relational algebra. Think of it like this. If SQL is the language we speak, relational algebra is the set of rules that gives that language its real meaning and all of its power.
Now, what's really fascinating is that SQL is actually a mix of two different formal languages. On one hand, you have something that just describes what you want, the end result. But on the other hand, you have the step-by-step process of how to get there. And today, we're going to focus on the how, the procedural part, which is our relational algebra.
Okay, before we can learn this new grammar, we need to get the vocabulary down. In the world of relational algebra, everything, and I mean everything, starts with a relation. And as you can probably guess, that's just a fancy academic word for a table.
I know the academic language can seem a little intimidating, but it maps directly to concepts you probably already know. A tuple is just a row. An attribute is just a column. See? At the end of the day, it's all just about tables.
The incredible thing about this grammar is that it's built from just a few really simple but incredibly powerful operations. So let's break down two of the most important ones. First up, we've got selection. The best way to think about this is like a sieve. You pour the whole table through it, and it only lets the very specific rows that you want pass through to the other side.
Let's look at a real example. So on the left, we've got our original table. That little algebraic expression in the middle, with the Greek letter sigma for selection, is basically telling the database, hey, take the results table and filter it down to only the rows where the student ID is 101. And boom, the result is that much smaller table on the right.
And here it is. This is the connection. That selection operation in relational algebra, it directly corresponds to the where clause in our SQL query. It's the exact same instruction, just written in a different language.
All right, next is projection. So if selection is about picking the rows, projection is all about picking the columns. It's kind of like a spotlight that only shines on the specific columns you care about.
So here, the projection operation, which uses the pi symbol, takes a table that has three columns, A, B, and C, and it spits out a brand new table that keeps only columns A and C. Column B just gets tossed out.
And in SQL, you guessed it, this is our select list. It's the part where we explicitly name the columns we want to see in our final result.
Okay, so these building blocks are pretty simple on their own, right? But their true power, I mean the real magic, is unleashed when we start combining them. This is where it all comes together.
We can picture these combined operations as an operator tree, and the trick is you read it from the bottom up. So first, we start with the entire results table. Then, we apply a selection to filter for just student 102. And then, on that already smaller result, we apply a projection to keep only the cat and eno columns.
So that whole nested algebraic expression, it translates directly into this one single clean SQL query that does everything at once. This is how we answer really complex questions, by building them up from simple, logical steps.
All right, so we've seen the theory behind the practice, but you might be wondering, why is it even important to know about this secret grammar? Does it really make a difference?
Oh, absolutely. This isn't just some academic exercise. It's the literal engine that powers SQL.
And here's the key takeaway. Because the database understands these algebraic steps, it can actually rearrange them to be more efficient. It can decide it's faster to do a selection first, to shrink the data before doing something more complicated. This is how it creates faster queries. It's the key to really appreciating the incredible engineering that's happening behind every single click you make.
So the next time you filter a search online, just remember that elegant algebra that's working hard behind the scenes. It's a great reminder that these powerful, logical systems are really the hidden languages that structure our entire digital world. Thanks for diving in with me on this one.